Hello students, welcome back. Let us resume our discussion in section 2. We completed subsection 2.1 and we were discussing subsection 2.2. We went through tautology and contradiction and we just discussed implication and equivalence. Did I say 90% of what we do in upper level math course is this? If P then Q is a tautology, or P logically implies Q. That's 90% of what you do. And the other 10% is basically this one. Logically equivalent. If P then Q, and also if Q then P. Both are tautologies. And of course, logical equivalence, that's basically this one put together twice. So you can pretty much say 100% of what we do is this. Is that important? Keep that in your mind, and let's have one more preparation before beginning something really interesting. There's some Boolean algebra associated to logical operations, and then I use the necessary and sufficient condition expression, or logically equivalent expression here, meaning this and that are equivalent, this and that are equivalent, commutative law, and so on and so forth. Contrapositive law, we went through those, and if you want to prove any of those, the best foolproof way is to devise that truth table and the final results are identical, and that's how you can prove anything. Okay, so much for the preparations, and let's talk about something important. Predicates and quantifiers. What is a predicate? A predicate is a proposition with one or more variables. So it works kind of like a function. Domain, we have a variable, so it works like a function. We have the domain, where the variable is coming from, and we have the range. The range is either true or false. Not both, not neither. So the range can take only two values, true or false. In bit logic, 0 or 1. I should have said 1 and 0 because 1 is true, 0 is false. Here's some examples. Let's define my predicate P of x as x is greater than 3. Then P of 4 is true, but P of negative 2 is false. You see, depending upon my x value, the truth value of my predicate can be different. Here's another example. We have two variables now, x is equal to y plus 3. 1, 2 is false. 1 is not 2 plus 3, which is 5. 1, negative 2 is true. 1 is equal to negative 2 plus 3, that's true. You see? So predicates work very much like a function. We have variable. So where is that variable coming from? We have to have a domain. And then the range of function values, that's rather trivial. We have true or false only. The domain is the important part. And in this case, x is greater than 3, so domain is probably some part of the real number, maybe the entire real number. It cannot be complex number, things like those. Due to the presence of the variable, some people call it propositional function, and yet domain, truth set, okay, all right. I talked about all those. Now let's talk about quantifiers. There are some quantifiers that you have to know. Universal quantifier for all. Here's an example. For all x in the domain, which is set of all real numbers, x squared plus 1 is greater than 0. Now, is this true? True for all x, a real number? Yes, it is. X squared plus 1 is always positive for all real numbers. How about this? X squared minus 1, that's not true for all real numbers. If x is 0, for example, this is not true. You see, P of x is true, Q of x is false. If you consider only this is true, or that is true, well, it depends upon your x value. But if you include this universal quantifier, then you're going to get truth or false of the entire predicate. Next, existential quantifier for some. For some real number x, x squared plus 1 is less than 0. For some real number x, x squared minus 1 is less than 0. This one is false because x squared plus 1 is always positive. This one is going to be true for some x, such as x is 0 or x is 1/2. They're infinitely many actually. So R of x is false, S of x is true. See the difference? For all versus for some. The algebraic part, x squared plus 1, well, that's pretty much the same, but we have completely different predicates. Next, uniqueness quantifier for one and only one. There exists one and only one x value in the set of real numbers, so that x squared minus 1 is equal to 0, and that's not true. 1 or negative 1, they're 2. This one is going to be true. Only one real number x, so that x squared minus 2x plus 1 is equal to 0. This is a complete square, so x equals to 1. That's the only one. Did I tell you that predicates were kind of like a function because it has a variable? Yeah, you have to consider the domains. Let's change the domain a little bit. For all real number x, x squared minus 1 is greater than 0. That's not true, but if I change the domain, for all x that is between 1 and positive infinity, you have different domain now. In this case, this is true. Even if we have the same universal quantifier, we have different domains, so we have different results. Q1 is false, Q2 is true. Here's another example. Instead of all real numbers, x squared minus 1 is equal to 0. For one and only one x, that's not true. We have positive 1 or negative 1. But if you have a little bit smaller domain for only positive x values, then yes, one and only one such x. And then there's some further terminology, binding variable versus free variable. If a variable is bound by some quantifier, we call it bounding variable, and otherwise free variable. I don't know whether they're going to be important in this course or actually any other math course, to tell the truth. Order of operation. Yeah, that's the order of operation. I hope everybody remembers. Let's see. How about some logical equivalences involving quantifiers? Distributive law. Okay, distributive law, okay. For all, universal quantifiers can be distributed in for conjunction and operation. An existential quantifier can be distributed into disjunction or operators, but not vice versa. A bit tricky, right? Commutative law for nested quantifiers. Universal quantifiers for all, I can change the order. Existential quantifiers, I can change the order. For all, there exists y versus there exists y, and for all, these are not commutative. And the third one here causes a lot of trouble to analysis students. In number theory, probably not much, but in analysis, this is a big deal, big deal. Associative law, let's not go too deeply into that. How about some negation? So all becomes some becomes all. Remember that? So when you negate, the predicate itself becomes negated. So for example, if you have an inequality, you have to flip it over. Greater than will become less than or equal to, things like that. But not only that, change the quantifiers. All becomes some becomes all. And then if you have conditional statement here, then you have to negate that too. This is not P or Q, so negate it using De Morgan's law. P and not Q, P NAND Q. Similar thing goes on. All becomes some becomes all, and you have to take appropriate negation. for any kind of predicate, and especially for conditional, things can get a little bit trickier, but they appear a lot in analysis. Here in number theory, probably a little bit too, probably not as much as analysis, but they do show up. Finally, negation involving logical implication. Oh yeah, okay, all right. Please remember the implication. If P then Q is a tautology, then that's tautology. That means true for all X in the domain. So you can rewrite this thing using universal quantifier. So if P then Q is tautology, or P of X implies Q of X, then you can rewrite it as for all X in the domain, P of X, then Q of X. So you can rewrite this double arrow using universal quantifier. That's a nature. And then if you negate, then you can negate this one. So for all becomes sum. And then this one here, if P then Q will become P NAND Q. P, but not Q. This, I think, will show up here and there in number theory as well. But they show up a lot, really a lot in analysis. Okay, so much for section 2, and let's meet again in section 3 in a separate video. Maybe several separate videos.